Hello, this is my part 1 for homework 7 in Digital Systems 423. So the first part of the homework was to create a 4-bit register that could perform the operation load and shift, and would hold the value otherwise. So to implement it, I needed several things. I needed a select input, an enable input, a clock, and a clear. Clear would automatically reset whatever the register was holding. It would automatically be 0000, no matter what. And I also needed an input to load into the system. I also needed a way for the user to view what was currently held in the register, so I created an additional output val, or output value. Alright, so first I created a signal so I can manipulate what was in the register's contents, because you can't manipulate or read an input, you can't read an output, you can't manipulate inputs and outputs, so you need a signal to do that. Then I check for a clock or clear signal. If I receive a clear signal, automatically clears whatever the register is holding, doesn't matter. Else it checks for a clock event on a rising edge, and if enable for the the register is active, it will check to see if it needs to load or shift left, depending on what select is telling it. So select for this one was 1-1 for load and 1-0 for shift right. Else it would just hold the value. And then you can see I assigned the current value of load to the output value. Okay, the next part was doing a counter. So the counter could increment and decrement, as well as hold its current value and load. And hold its current value. So I needed several signals again. I needed an input, an enable, a clock, a reset, an input, a cout, so I could see what the current value is like if we had to display to a 7-segment display. And that's pretty much it. Then I create a signal counter to manipulate what the count currently is of the counter. So it automatically starts at 00 and can count up to 16. After that, it will loop back to 00. So first it checks if reset's inactive. If it's reset, the counter goes back to 0 regardless of whatever else is on it. Select determines whether I increment or decrement or hold the value. If I receive 0-1, it will increment by 1, else it will decrement by 1. And then else it will hold the current value, so counter equal to counter. And then I assign the output count to counter, so I can see the signal on top level and above. Alright, so on my top level, I just implemented all 3 of these, including my FSM. Before I go on to my top level, my FSM, how it works. So the FSM controls both the register and the counter in this homework, and determines when one does the operation and one doesn't do anything. So it has a clock and a reset as input, and a select and an enable as an output, as well as a reset signal for the rest of the system instead of itself. So it uses the current state and the next state. So I have about 6 states, give or take, that it goes through to do what the homework tells it to do. So first it checks if you have a reset. If the system is reset, then the current state is equal to 00. Else, on a rising clock edge, the current state is equal to the next state. And then with the next state logic, I assign values pretty much as a Moore machine. It doesn't depend on the input to determine what the next state is. So in the first state, it will reset everything. So it sends a reset signal to the rest of the system, clearing whatever's in the register and also the clock, resetting it to 0. And then it moves on to the next state. It also sends out the signal 00, so neither of them do anything. And it also, yeah. Okay, I also have another signal So after everything is reset, I increment by 1, then I increment again, then I send a de-increment signal to the counter, and then I load the register, then I shift it left once, then I shift it left again for twice, and then it will continue to shift the register. Otherwise, it will if the FSM receives a reset signal, it will start back over at the very first case. However, I have to do when others, and obviously you're not supposed to be here, so if you do somehow get here, you'll be sent back to the first state. So in the top level, I just implemented all 3 of these components into one system. So all the top level needed for inputs was a clock and a reset, and a valve and a count so I could see it in the test bench, as well as a select and enable so I could also see them in the test bench as well. So signal-wise, I have 4 different signals that interlace through each of the components. As I reminded before, this is the reset for the counter and the register. This is the select for the counter and register, and the enable, as well as the input for both of them. The counter, here's its component initialization, and then here's when I implemented or initialized the components. That's pretty much it for the top level, besides letting myself see select and enable on the test bench with this line right here. So on the test bench, I recreated all the signals needed for the top, so I could see everything going on. After that, I created a component of the top level, and then I created an instance of it. Then I began a process with a for loop. So the for loop would just act like a clock, basically, and change the values over time. So you would see clock go up and down with the least significant bit, so it's the fastest. So clock edges happen twice as fast as the next significant bit. So the clock will go up and down 16 times, or it'll have 8 active edges. So, and that's all we need to see that the FSM is working properly. And we send a reset to the FSM so that we can properly establish that all the components are at 0, 0. And it waits 10 seconds between each loop cycle. This helps me make sure that I can assign the least significant bit to clock, so I can iterate a clock. So let's go ahead and get to the waveform. So in the waveform, you can see that the test bench worked properly, that I established all the signals properly. So I'll walk through it. So right here, I reset everything, so it's all reset. So this is the first clock, so this is the first state. Then on this, it moves to the second state. So as you can see, count is now 1, so it incremented by 1. Then on the next clock edge, it increments by 2, then it de-increments by 1, so that works properly. And then on this clock edge, it switches from paying attention to the counter to the register, and then it loads the value I preset in the test bench, the top level. Right here, I set the value of the input for the register to be 6, so I could easily see the manipulation. So it loads it in, then on the next clock cycle, it shifts it by 1, because 0, 1, 1, 0 when shifted becomes 1, 1, 0, 0, which is another translation for C in binary. And then it shifts one more time, and then it becomes from 1, 1, 0, 0 to 1, 0, 0, 0. So the shift left works properly, and that is pretty much it for the code, and my FSM is working properly. Thank you so much.